All right, resistance in Ohm's law. So these are the objectives. It's C.1.B.1, 3, and 4, and you'll have your objectives list to refer to that. We did the 2 C.1.B2 in the last lecture. So understand conductivity, resistivity, and resistance so that you can relate current and voltage for a resistor. That's the simple equation that most people mistakenly call Ohm's law, V equals IR, and we'll see where that comes from today. And describe how resistance of a resistor depends upon its length and cross-sectional area, and apply this result in comparing the current flow in resistors of different material or geometry. So basically, how does the resistance of a resistor depend on its size and shape and material? And number 4 is kind of similar. We're going to come up with an expression for the resistance of a resistor of uniform cross-section in terms of its dimensions, so area, length, and the resistivity of the material. All right, so let's move on. All right, so most people that are aware of Ohm's law think that V equals IR is Ohm's law, but that's not what Ohm's law is. And what Ohm's law is says that for many materials, including most metals, right, that we build a circuit out of, current density, J, which we learned about in the last lecture, is proportional to bigger the electric field inside a wire, the more current density. Right, and that should make sense. So the way we express that in the equation, E is equal to some constant times the current density J. Right, that's what if something's proportional, and the constant, we use the symbol lowercase rho, and we call that the resistivity of the material. Right. And you can look at that equation. If resistivity is really big, then you're going to need a much bigger electric field to get the same amount of current, right? Because it resists current flow. If the resistivity is really small, then you don't need much electric field to get that same current density. All right. So a material is either ohmic or not ohmic. For ohmic materials, this constant rho is actually constant. I guess I shouldn't call it a constant because it's only constant for ohmic materials. And that's why that goes along with up top, right? For many materials, current density is proportional to the electric field. Those are the ohmic materials. For non-ohmic materials, rho is not constant. Right, so it might depend on the temperature. It might depend on the potential difference. It could depend on a lot of different things. Yeah.
What do you mean by like constant and not constant? Is that like a number value?
Yeah. So for a material, so say copper, we can look up the copper's an ohmic material. You can look up the value of the resistivity for copper, and that's the resistivity for copper. It will change slightly based on temperature, but not so much that it's important for us. For something like, I don't know, any other material that, for example, I think a light bulb is pretty non-ohmic. So, you can put a light bulb in a circuit, but if you measure well, we'll also see that if the resistivity is not constant, the resistance itself is not constant. So the resistance and the resistivity of a light bulb is going to depend on how much, what the potential difference. If you put a different battery, you might have a different resistance. But for an ohmic material, that's not true. You're just going to have a resistivity that doesn't change based on temperature very much, or potential difference, or size and shape, or something like that. Does that answer your question?
Yeah. I
We're,
was just thinking like math. So like a constant would just be like a value, like a number.
yeah.
I didn't know how that would look like for this situation.
Yeah. Well, so there's a table in section 27.2 in Sir Wayne Jewett that gives you the resistivities for various metals. you can't make that table for all materials, because for some materials it's going to change depending on the shape and the size, or what battery is your circuit, or and how hot it is.
Yeah.
So you just can't list a single resistivity for a non-ohmic material. But we're mostly going to be looking at ohmic materials. The first lab we're going to do, we're going to look at a few different resistors, light bulbs, LEDs, things like that, and try to figure out which ones are ohmic and which ones aren't. Basically, by doing this, seeing if the resistance changes when we vary other things. You've seen, I know you've already mentioned sigma, right, in the Surway and Jewett book, conductivity. Conductivity and resistivity, we don't need both quantities because one's just the reciprocal of the other one. I guess it's worth knowing that you can use both, but we're really only going to be looking at the resistivity here in this class. And I think the AP test won't ask you anything about conductivity, just resistivity. But they are reciprocals of each other, so if you know one, you know the other. And that makes sense too, right? Resistivity is how resistant this circuit element is to current flowing through it. So more resistivity means less current flow, right? But conductivity means it more conductivity means it conduct more current. So large conductivity means more current flow. Okay, let's go on. See where resistance comes from. So we're going to look at a section of wire, just like we did in the last lecture, cross-sectional area A. We'll give it a length L as well. And we'll put a battery across it so that there's a potential difference across the end of the wire. So there's going to be current flowing in it. Right? Remember, potential difference, you can think of it as a hill for charges to roll down, right? The potential difference on one side of the wire is higher than the potential on one side of the wire is higher than the potential on the other side of the wire, so charge is going to move from one side to the other side. So cross-sectional area A, we're going to call it length L. So if we assume a uniform electric field in the wire, and we usually do when we're talking about current flowing through a uniform wire that doesn't change its, that's constant cross-section. What we know is that the potential difference, and we did see this when we talked about potential difference, or the magnitude of it, is just going to equal the electric field times the length. And that has mostly to do with the fact that electric field is the derivative of the potential. So that means that if we use the equation we just had for conductivity and plug in for the electric field, we're going to get that for ohmic materials, at least, we're going to see that our potential difference, and I'm dropping the absolute value sign, is resistivity times current density times L, the length of the wire. Right, I'm just plugging in from what I showed you on the last slide that electric field is resistivity times current density for ohmic materials. So I'm going to rearrange that a little bit, or actually let me plug in for current density, which I know is just current divided by area. All right, so if I come down here, I can say potential difference is the resistivity times current divided by area times the length of the wire. And now I am going to rearrange this just a little bit so that I get this ratio, the potential difference. I'm going to divide both sides of this equation by current. That means I'm going to have potential difference is the resistivity times the length of the wire divided by the area of the wire.
Why'd you divide by the current?
Because what I'm going to do next is define resistance of a circuit element. And this is true for anything, ohmic material or not. Resistance is defined to be the potential difference divided by the current. All right, so any element in a circuit, if you can measure the potential difference across it, and you can measure the current flowing through it, and the resistance is defined to be as the ratio of those two things. This is a very important equation. We're going to use this all the time. Very useful, very important. A lot of people call it Ohm's law. It's not Ohm's law, but you'll hear it referred to as Ohm's law. but this is just the definition of resistance. So for ohmic materials then, we have a nice equation for the resistance, right? If resistance is defined to be potential divided by current, and for ohmic materials, potential divided by current is this resistivity times the length of the wire or circuit element divided by area. That means for ohmic materials, our resistance is just equal to resistivity times length. All right, so going back to the objective, right? This is how we can relate resistance to the cross-sectional area of a wire, the length of the wire, and the resistivity of the material. So if we look at the equation for, so resistivity, the rho, that depends on just what material the object is made out of. So the resistivity comes only from the material. But the resistance, if we look at that equation, resistivity times length over area, the resistance also depends on the size and shape of the resistor. All right, so
What's the difference between resistivity and resistance?
the difference is that everything made out of copper is going to have the same resistivity, but depending on the shape and size of its cross-sectional area and the length, they're all going to have different resistances. A longer wire is going to have a larger resistance than a shorter wire, all else being equal, but they'll have the same resistivity because they're made out of the same thing.
They have the same resistivity, but depending on the size, that's when the resistance changes?
Yeah, it'll be shape and size, yeah.
Okay.
I mean, when we open up our resistors for our circuits, they all look the same, except for the different colored bands. But inside, the high resistance ones will have a much narrower, path for the current to flow, basically. But yeah, that's an important difference, right? Different resistors might have the same resistivity if they're the same material. Resistivity you basically look up based on material. Resistance you would calculate based on resistivity, length, and area. Almost done here. A couple things. What would the unit for resistance be? The unit is the ohm. The capital omega is the symbol that we use for ohm. And what do you think of ohm is defined as? And we can just look at the definition of resistance to figure out the definition of our unit. If resistance is defined as potential divided by current, what's the ohm got to be equal to? What's that? Well, potential, what's the unit for potential? Which we also call voltage. What would the units for voltage be? Volts. Yeah, potential difference is volts. And the unit for current? Yeah. So an ohm is just a volt per ampere. Or volt per amp. So on just one thing, because moving forward we're going to take a look at some ohmic materials and some non-ohmic materials and try to tell which is which. If we were to graph, let me make a quick graph here of, I can change the potential difference across my resistor and measure the current through it as I do that. For an ohmic material, what is that graph going to look like, do you think? Because an ohmic material, the resistance is a constant, so that proportionality, delta V over I, is going to be constant. So if I graphed current versus potential,
It would just be a linear?
it would just be a straight line, right? Because if I graph current versus potential difference, the slope is the resistance, right? Because rise over run, I've got delta V over I. So for an ohmic material, if you measure the current at a bunch of different potentials, you should get a straight line when you plot it.
Would it be like a straight line with no slope or a sloped line?
So no slope would mean, the slope of 0 would mean a 0 resistance, right?
Yeah.
So if you had a perfectly conducting material, which doesn't really exist, but you can get pretty close, then you'd have a 0 slope. But any kind of real resistor, it's not going to be 0, right? As long as you have a resistance that's not 0, then you'll have a positive slope.
Okay.
And then just for comparison, if I have a potential versus current of a non-ohmic, come on. I'm going to have to figure out how not to do that. Then it would just not be a straight line, right? It could, it's probably something, oftentimes you'll see something like that, right? So this would have a low resistance when there's low potential because that slope is pretty flat when potential is low, but this object would have a high resistance when potential got higher as well, right? So the slope's not constant, the resistance is not constant, so you have a non-ohmic material. All right. But let's just mark on here that slope is resistance. We're going to be making graphs like these in our first circuit lab.